Hello, it's me, Krishna Pokhrel, and today we are going to learn about how to study the half-life of a given radioactive substance in our physics laboratory. Okay, we are going to know about this experiment. Okay. To study the half-life of the given radioactive experiment, we need three different apparatus. Okay, along with this, we may need the other one. I'll show you in figure. At first, we need a GM counter tube. Okay, and a counter and a radioactive source. In our context, we took cesium 137. Okay. Before starting this experiment, we need to know about the half-life. What is the half-life? Okay. As the term half-life, okay, it is very clear from this um, simple word, okay, half-life. The half-life of a radioactive substance is the time required for half of the radioactive nuclei to decay. Okay, time taken for half of the radioactive nuclei to in a sample to decay. Okay, in a simple context we can say um, at how much time, okay, the radioactive sample gets into its half, okay, from the original size. Okay, that is called a half-life, the time taken. What type of radiation can be emitted during a radioactive decay? Okay, the radiation are alpha particle radiation, beta particle, and the gamma rays will be radiated, and hence the particle will be decayed to um, in the process. Okay, now in this context we need a GM tube. Okay, here is a tube which is inserted in this place, and below this tube, we have kept one cylindrical vessel. Okay, actually, this tube is a GM tube. Okay, I'll come to this later. And this is a GM counter, and this is a cap. Okay, which contains radioactive substance. Actually, it is stored inside this, but in order to display, okay, I have used this cap to capture a photo. I kept outside, and this is a solution. Okay, I'll show you the process how to take a measurement. Okay, these are the substance which we use in our laboratory, and a power source of 220 volt to operate this device. Now actually, our observation will be like this. Okay, before starting our observation, we will take the radiation reading with the counter. Okay, with the help of counter and a GM tube without any source. That means we will on this mechanism we'll set up this GM counter tube. Okay, and after this, when I zoom it little bit further, okay, we can see here on off state of a bottom, okay, which gives the buzzer sound, and this is the power of this counter, and here is the backlight. Okay, and here we will set it whether we will measure count per minute or count per second. Okay, and the other one is MSB per hour. We'll set it into this format. So after that, in order to take a radiation measurement without any source, we will remove the source from this place, and we will just remove this two aluminum sheet also where the source is kept, okay, in this small container. At first we will um, on this device, and we will take this GM tube in this position. Without this to sit, we will adjust this GM tube, and after that we will take a reading for several minutes. Okay, here we have took 10 different reading, and we have this reading without any source. That means the background radiation reading. Okay, we'll keep the source far away in this case. Okay, we'll not keep the source here, we'll keep the source far away and we'll take the measurement. And after that we'll get the value for the average value of this reading, that is equal to 101.6 in our context. So now what happened is the next part, we will start the same measurement with the source. Now I will tell you how to keep this source in this measurement. We have this solution. Okay, this solution is mostly consist of sodium hydroxide and HCl. Okay, and this is a mm, another device which will soak this solution, and it helps to deliver this solution into this small container. So at first we will there will be a small mark, okay, up to that is the for the measurement of this container. Okay, how much liquid will be adjusted in this small container. Okay, for this it is kept a mark. You can make the measurement in your own context also, little bit. Okay, up to more than half of this container should be filled with this solution. So we'll take the solution in this small container. Okay, that is what do we call that, sucker. Okay, that sucks this solution, and through this nozzle, okay, we will keep this small container outside and keep this cap over it. Okay, and deliver this solution through this nozzle into this part, and the solution will be finally into this container. Okay, in this process, okay, we have this solution, and this solution will be delivered through this cap. It means that this cap consists of radioactive substance, so that the solution that contains a radioactive substance will be finally delivered into this small container. So now after that, we'll keep the container over here. We'll keep this aluminum sheet. The upper one aluminum sheet have a small hole, so that the radiation coming from this radioactive substance solution will be finally ejected through this GM tube, and the radiation reading will be set in this counter. Okay, it is adjusted in such a way. It is simple experiment, and after that we'll take a different reading. Okay, time in second for every 60 second, that means for every 1 minute we'll take a reading. Okay, this is the reading n dash, actually it is n dash. This is the reading which is delivered by this system with the help of source, not without the source. Okay, these are the readings without the source. The A number one is the reading without source. Now, what will happen is we need to subtract the background radiation reading, because in this context, okay, there is the influence of background radiation also. So before we have taken the mean of several data, so we'll subtract this value of B from n dash and we'll get the value of n. Okay, and after that we'll get the value of log n and set that value is equal to y, and this is the value of x. We'll get the x square, xy, and y square. These are the required terms for the several calculation. So now whenever we plot a graph between time and log of count rate per 10 second, okay, actually this is minute, but here we have divided and taken it in 10 second. You can place it in 10 minute or 1 minute also. Your data is for 1 minute. Okay, this is not a very lengthy process, but you can use whatever you like. Okay, log of the reading, and you will take here the time. Actually, you will take the reading of this value of n, okay, not n dash, because it is the corrected value of count. So now we'll get this type of graph. We'll take a best fit line, and the line will be as shown. Now, our main intention was to calculate the half-life of the given substance. Actually, till now we have taken the observation, and we have plotted a graph. Now, how to take a half-life reading? We have this formula, okay? Actually, we have the formula for n number of atoms after time t, okay? The formula will be n is equal to n naught e power minus lambda t. That means after time t, the number of atom will be decayed to the n number of atom. Previously, there were n naught number of atoms, and after time t, we'll get the n number of atom. This is the simple formula for the half-life, and we have the formula for time taken for half-life is log 2 by lambda. That is equal to 0.693 by lambda. Now, if we have the value of lambda, we'll take the, no, we will finally get the value for half-life. So for this process, we will need the value for m. M is actually the slope, okay? M is actually the slope of this straight line, okay? In this context, we have taken the slope by this formula, n summation of xy, summation of x, summation of y by n summation of x square minus summation of x whole square. Okay, I will tell you what is the value of n. N is the value for number of readings. Okay, actually here I have only shown the sample for reading. For data, actually we have the 30 different reading. That means for 30 minutes we have taken this reading. That means the value of n will be 30. And simple calculation for summation of x, summation of y will find out about this. Summation of x is if you sum this data, okay, if you add these all, you will get the value of summation of x. This is x. If you add these all, you will get the value of summation of y. If you add these all, you will get the value of summation of xy. Every data can be calculated and we'll get the value of m. Okay, m is actually the slope. Now we have finally the formula to calculate the decay constant, that is equal to negative of slope. Whatever the value we get here, okay, if we apply it over here and give a negative value to that slope, we'll get the value for decay constant. If we apply this value of decay constant in equation 2, then you will get the half-life of that substance easily. So I hope it is clear to you, and I have completed my experiment, okay, explanation of this experiment. So after saying this much, I would like to end, and if you have any kind of question, then you can raise it in comment section. Okay, we'll see you again. Bye-bye.